All right. So to review for the exam this year, I decided to make my own 2025 practice tests. And here we are with the E&M free response. I gave this one out in class, and it was pretty agreed upon that this was a really challenging set of questions. So this is a really good test of how you could do in sort of strange scenarios or something non-typical with a lot of these setups. But feel free to try this on your own and then kind of look at the solutions or watch the video. All right. So first we have question 1, which is the mathematical routines, or MR. So I know this is going to be derivation based with some sort of figure to draw on. So question 1 says the diagram shown above has a square conducting loop of dimension S and resistance R moving through a long region of magnetic field out of the plane of the loop, which is pretty normal setup, except for the fact in this problem we see that the magnetic field is getting stronger and stronger out of the page as the loop moves to the right. And it's important that there's an external force pulling it, and it's moving it at constant speed. So now we're going to look at part A, which says consider a moment in time when the loop is at some position greater than 0 while being pulled to the right. So just somewhere as it's actively being pulled in this field. We're just going to draw ourselves a free body diagram for the loop at this time, just with magnetic forces. So figuring out what magnetic forces are acting on this loop on all 4 of its sides. So first, we're going to have to utilize Lenz's law to figure out the direction of induced current. So if this is my conducting loop, I know that the magnetic field strength is out of the page and it's increasing. So I know that the field is increasing out of the page right now. So as a result, we need to create a into the page B field from the induced current. And into the page that's generated by clockwise currents, or just use your right hand to do that. So we know that this is the direction of the induced current throughout the loop. So it is going to be clockwise. So that still doesn't help us figure out the forces, but it at least tells us the current. And we know that a current carrying loop in a magnetic field will also feel a force, because we have the expression that the force on a current carrying wire is equal to IL cross B. But we usually simplify this because in almost every situation, I just call this the Bill force. And actually, I should make this a lowercase l because inductance could show up in some way. So to figure out the direction, we just cross QV and B. And again, I consider I the same thing as QV in this situation because it's just the motion of positive charges. So that's what current is. So we just QV cross B each side of the loop to get the force. So if I do QV cross B with the top of the loop, just remembering that our current is doing this. So if I put my thumb to the right, starting with the top of the loop, my thumb to the right, and my fingers pointing at me, well, that makes my palm point down. And actually that tells me what direction all forces are. You can see that that's actually going to mean all forces point into the loop. So you can try that for each side. So pointing your thumb in the direction of current and pointing your fingers at you, and your palm will always point towards the center of the loop. So now we got to deal with the magnitudes of the forces here. So first, notice that in this situation, the B field is actually stronger on the right side. So this means there is a stronger magnetic force on the right side of the loop compared to the left. So when I draw my diagram, it matters that I show there being a stronger force on the left versus the right. Or sorry, on the right versus the left. And then I'm just going to make my vertical forces sort of an intermediate between that. So the actual numbers don't matter. But what we see is that the magnetic force does cancel vertically due to symmetry. There's no winner here. But it doesn't cancel horizontally, which makes sense, because Lenz's law tells us that this Bill force is always going to resist the flux change. So if I'm trying to push it further and further into this magnetic field of increasing strength, it should be feeling this sort of resistive drag type force that's going to be to the left, trying to keep it from increasing its flux. So now we can just go in and actually solve the problem where we want to figure out how hard we have to pull on the loop in order to keep it at constant speed. So for our point breakdown, this free body is just 2 points. So you get 1 point for all forces being pointed to the center of the loop. And then you also get another point for canceling the vertical forces and leaving a net force to the left. So again, if everything points towards the center, that's 1 of your 2 points. And if you have a net force to the left, that's a second point. Now we're going to find the force that you have to pull the loop at in order to keep it at constant speed v. So we always start from a physics principle / reference book equation. And here we know that it's constant speed. So I'm going to just start from Newton's second law and say that the forces have to balance. And in our case, we saw above, there's this Bill force that needs to be balanced out by our pulling. So I know that my net external force F has to equal the net magnetic force acting on the loop. So now let's find those forces. So we know that the magnetic force acting on a current carrying wire is going to be IL cross B, which we have been referring to as the Bill force. And the L is definitely just going to be the side length here. So before we can do anything productive and deal with the subtraction, we need to figure out what the current is in the loop. So first, we know this is an induction problem because I'm moving in a B field. So I should definitely start from Faraday's law, where the magnitude of the EMF is d flux dt, which is the derivative with respect to time of the B field times the area. Nothing weird happening with the angle, so I'm not including the cosine term. And in our case, the area is staying constant, but the B field to the square is going to be increasing. So I can just write this as the area times dp dt. The area is just s squared. And then my B field increased via the relationship alpha times x. And then applying the chain rule on this, we get this as alpha s squared dx dt, which is the same thing as alpha s squared times v. So taking a moment here to pause, this should make sense qualitatively that this is an expression for the induced EMF because it gets stronger with a bigger loop and it gets stronger with a bigger velocity. So it should depend on both of those things. So now we can find our induced current in the loop just via Ohm's law. And then we can find our answer. So our net external force we need to apply is going to be the magnetic field on the right side of the loop, which would be that x plus s, because we want the loop when the left side is at a position x, times the induced current times the length, and then we subtract off whatever the force was at the left side of the loop. So we can actually factor out this entire expression of the induced current and S, because that's the same. So I can factor out alpha S cubed V over R. And then B of X plus S would be alpha times the quantity X plus S. And B of X is just going to be alpha X. And we can see that I get alpha X plus alpha S in the parentheses, so that alpha X actually cancels. So we get alpha S cubed V over R times alpha S. So after canceling these terms, we just get alpha squared S to the fourth V divided by R. So a rather tricky Faraday slash motional EMF problem there. So now for the points. This one is out of 5 because it's a big derivation. First, you will get a point for identifying that the net force must be equal to 0, slash the net force has to be given, the net output force has to be equal to the net magnetic force. So anything on this top line earns that point. For your second point, a correct expression for the force on a current carrying wire. The third point, for correctly finding the induced EMF from Faraday's law. The fourth point, a consistent substitution into an Ohm's law expression for finding the current. And finally, the fifth point comes from a consistent substitution into a subtraction of magnetic forces between the two sides of the loop. So if your EMF is wrong, you could still earn the latter 2 points in this derivation, as long as you plugged into I equals EMF over R, and then worked that out by plugging in and evaluating the magnetic field at those 2 times. I'm sure there's an alternate solution to this problem. I know I first approached it by just finding the flux, then differentiating. There's lots of ways of doing it. But essentially, you're just finding the bill forces and finding the net between the 2 sides of the square and hoping, and saying that your force will cancel that. So I think most of these points are actually gettable, even though this was a very challenging problem to entirely do correctly. So this would be out of 5. And now part B is always unrelated, but somehow connects to the original scenario. It doesn't depend on anything else, though. In a different scenario, the same loop is placed at rest in a uniform field that's initially perpendicular, but then you rotate the loop such that the component of B piercing the loop varies according to this cosine function. So we are going to derive, but do not evaluate, an integral expression that would yield the total energy dissipated after 1 revolution. So we want total energy. So I know that power is the rate of change of energy. So power is the rate of change of energy. And in the formula sheet, we see I delta V is our expression for power. But when dealing with EMF and induced currents, typically we don't want to do that extra step of finding current. So if I use the fact that delta V is IR, or current is EMF divided by resistance, I could get EMF over resistance times EMF, which gives me this alternate power expression of EMF squared divided by R. So I'm going to first just find the power outputted during this process, because that at least gets me the rate that energy is being dissipated. So the EMF, once again, is found by Faraday's law, because we have a changing flux. And in our situation, we have a constant area, so this would just be area times dB dt, because it's differentiating B times A. And the area is S squared because it's a square, and the derivative of the cosine curve would be negative sine of 2 pi over the period times t times that chain rule factor of 2 pi divided by the period. So there's my EMF. And now I can actually just plug in. So the power would be equal to the EMF squared divided by R. And I'm not done if I plugged that in for EMF, because actually what I want is the total energy dissipated. So to find the total energy dissipated, you need to integrate all of the little contributions to power with respect to time. So I'm integrating from 0 to t, because it said 1 revolution. And my expression for EMF was going to be negative s squared times 2 pi divided by capital T times sine of 2 pi divided by the period times t. That entire thing gets squared, and then I divide by r with respect to time is the integral. And that's actually the answer. So this huge mess right here is actually our final answer. Although, oh, please do not simplify this, by the way. Do not actually do the squaring, right? It was a do not evaluate question. Do not trust your algebra skills. Just leave it like this. Although I definitely imagine that even indicating that your EMF from up here needs to be plugged in is sufficient, but I would just actually write it out. So the part B derivation's worth 3 points. So first, you get a point for a correct relationship for electrical power that you substitute into. So that would be EMF divided by EMF squared over R if you substitute in. So let's say my first point would be a derivation that begins from Faraday's law that gets the correct EMF. So the correct EMF is worth 1 point. Not counting sine, because I always ignore the sine in Faraday's law, because EMF's really just a magnitude thing. So the first point is that correct EMF. The second point is a correct statement of a power formula. And the third point would be a consistent substitution into an integral of a power formula with limits. So if you substitute in, it has to be from 0 to capital T, as long as you substitute into that power expression. So that's your 3. So again, just looking back, question 1 is worth 10 points entirely. So we got 2 for the free body diagram. There's 1 point for all of the forces pointing towards the center of the loop, and there's 1 point for the net force pointing to the left. For our derivation, we got 5 points in total there for the net force required. And then for our mini derivation for part B, that was worth 3. And also, you can see with E&M, you're going to have a question on induction, magnetism, circuits, and electric fields. So notice that was the induction question. So we got what I think is the hardest one out of the way first, because induction was matched with question 1 in this case. So that's the mathematical reasoning question, where it is just classic derivations with a small diagram. Now here's the one that tests the most skills. It's question 2, the translation between representations, which has us looking at multiple skills, sort of diagramming, deriving, graphing, and comparing. So here, this is, on first glance, it could look like Gauss's law, but actually if we look at it closer, we see these are current carrying cylinders. So it's actually going to be an Ampere's law question, or a magnetic fields question. So we have a coax cable. It's comprised of concentric cylinders with currents in opposite directions. So the inner cable has a uniform current density J0 into the plane of the figure. So this has a magnetic this has a current into the page, and it has a constant density, J0. And then the outer cylinder carries a current out of the page and has this sort of increasing current density given by J0 over 2R times R in the opposite direction. And we're going to be asked all sorts of things about this setup. So first, we want to find the magnetic field direction at each of these spots. So first, it's pretty easy to get the one at the center. We do actually have to write it, though. At the center, there is no enclosed current, so there's no magnetic field. I'll actually write this down here, because I'm going to need space above. All right, that's your first of the 3 diagramming points. Then your second point comes from drawing the correct magnetic field right outside. So to find magnetic field, we know that it orbits around wires. So to do that, I would draw yourself a radius from the center of the wire to the point, and then figure out what way it needs to actually orbit via the right-hand rule. So in our case, this current is into the page in the center cylinder. So if I stick my thumb into the screen and wrap my fingers around, this is once again clockwise. So I am just going to draw myself an arrow that is directed in the clockwise direction at that point. And then we're going to look further. So we draw ourselves a radius extending further outside the wire. And here's where we have to do some thinking, because these currents are in opposite directions. So I actually could get any of the 3 field directions, clockwise, counterclockwise, or 0, depending on how the currents compare. And actually, in our case, we have a current of J0 times pi r squared in the middle wire, but in the outer wire, it increases in density, and it has a bigger area. So even if I plugged in the lowest density, which would be the value at 2R, it's still more dense than the original current carrying cylinder. So this actually means that the outer cylinder ends up winning out, so the field direction flips. That's kind of hard to see, which was an aspect of the problem that I intended you to have to think about, is the fact that you will actually get a flipping of the field direction. So you get 1 point for each of these. Seems to be my initial grading scheme. So that's out of 3. Next, in the region 2R to 3R, derive an expression for the distance where the magnetic field is equal to 0. So there is exactly 1 spot between the 2 inside this shell where the field is equal to 0. So we got to figure out what that magic place is that we exactly cancel out the current. So derive an expression from the distance center where it's equal to 0. So I know that this is about enclosed current. So I can relate the fact that Ampere's law tells us that the integral of B dot dl is equal to mu naught over I enclosed. And we actually don't need to use Ampere's law for this problem, because if B field is equal to 0, that means that the enclosed current is actually equal to 0. So what this tells us, if I plug in 0 for B, this tells us that the enclosed current is equal to 0, which tells us that the inner and outer currents have to cancel. So now let's calculate each of those. So first, for my outer current, this one is the more complicated one. So for the outer current, I can just integrate the density function with respect to area. from 2R to R. So this gives me the current in the outer shell. And then I can subtract off the current in the inner shell. And that's constant, so I can just use JA as current. I don't have to integrate because every current segment had the same amount in the innermost wire. So now I can just do some substituting. So integrate from 2R to R of J0 over 2R times R. And dA is 2 pi R dr, so don't forget that you can't just integrate with respect to R. You have to use the fact that if we have a circle, a tiny area slice of that circle is a thin circular ring. And then we just had a radius of big R for our inner wire, so J times pi R squared was that current. All right, now we just simplify. So I can pull a J0 and a pi and a big R out of this integral. And then I'm left with R squared, so I end up integrating R squared, so I get R cubed over 3 from 2R to little r. Then simplifying some more, I'd get J0 pi over 3R times R cubed minus 8R cubed, because 2R quantity cubed becomes 8 times big R cubed, minus J0 pi R squared equals 0. Then doing some simplifying / fraction clearing here, we see that everybody brings a J0 pi. And then I'll just multiply every side by 3R to clear that denominator. So I'd get R cubed minus 8 times big R cubed minus 3 times big R cubed is equal to 0, which tells us that little r cubed is equal to 11 times big R cubed. So little r is equal to the cube root of 11 times big R. Which is quite challenging. I really like this part. I thought this was a really interesting result, and the fact that it worked out not terribly, even after all the algebra. All right, so here's how your 4-point derivation was split up. So you got 1 point for relating the B field to the enclosed current. You also got 1 point for indicating that the enclosed current being equal to 0 implies that the differences in the inner and outer currents must be equal to 0. You got a 3rd point for an expression, for a correct expression that could give the current in either cylinder. So either an integral in the outer ring or just the JA for the inner ring was sufficient to earn point number 3. And all of the algebra leads to a correct answer for your 4th point. Again, the algebra will not usually be many points at all, and in this case it's only 1. So after I set up all the calculus, all that simplifying to get to cube root of 11 was only the 4th point. So this is out of 4. Now we come to the most interesting part of this question, I think, and that's actually coming up with the magnitude of the B field as a function of R. So inside the current carrying cylinder in the center, it increases linearly. That's because you're getting quadratic increase in area, but you have to spread the circulating B field over a ring that increases like 2 pi r, so you end up with a linear relationship. Or this is just something I tell my students to memorize. Inside a uniform insulator, electric field increases linearly, and inside a uniform conductor, B field increases linearly. Then we know the field is going to decrease outside of the wire. But actually, once you reach the second wire, it still continues to decrease, but it actually decreases even faster. So you get this sort of non-differentiable part here. And then we know we hit 0, and we know we hit 0, and the field increases as we get that more and more dense current before decreasing once again outside the wire. So we get this weird graph shape, and we're not grading for heights here because it's not labeled, but I do know that my height needs to be taller than the original, just due to how the area works out. So here's your 3 points. So first, you get a point for this region. So a linear increase and then some sort of a decrease. So you get 1 point for what the graph looks like between 0 and 2r. You get 1 point for your graph having a 0. And then you get 1 point for a decreasing b when r is bigger than 3r. So again, nothing about the heights matter. So your first point was for the linear increase and then decrease. Your second point was for hitting a 0. And your third point was for showing this decrease outside. Then we have to indicate whether our graph is consistent with our field vectors. So we said that there's no field in the center. Then the field flips direction somewhere between the cavity and the outside. And do we see that? Well, yeah, we do, right? I have 0 field at the center. Then my field is non-zero. Then my field hits 0 and comes back up, which is reflecting that. So I'm actually not too picky with how we'd grade part B. So first, you just have to say whether it's consistent or not. So I said, yes, it's consistent. And there's no magnetic field drawn in, at the center of the cable, which is shown by the graph passing through the origin. And I actually would say that's acceptable. You could stop it there and get your 2 points. So first, you get a point for just for saying if it's consistent or not. And you trust that the grader will know if your answers are consistent with each other or not. So that's your first point. And then your second point is a relevant justification. And I also went further with mine and showed that I said, well, my picture is showing this magnetic field direction change. And I see that's happening because there's a 0 that exists on my graph. And we don't actually see the sign change because we didn't graph like a direction. We just graphed the magnitude. So that's out of 2. So summing this up, we get the 3-point diagram, the 4-point derivation, the 3-point graph, and the 2-point consistency check. And that gives us 3 plus 4 plus 3 plus 2, which is out of 12. So this is the long question. And now we're on to the ones that are at least more familiar. So our lab question, question 3. In experiment 1, students wish to calculate the resistivity of the material inside a large cement-filled resistor in the shape of a rectangular prism. The students have access to many resistors that look like this. We have wires that can be, we can wire these together. And we have a multimeter capable of directly measuring resistance. So with these design your own experiment questions, it is definitely given to you what materials they're intending for you to use. So I see I have many resistors, I have a ruler, and I have a multimeter for resistance. And another good thing to do is almost like let the equation guide your experiment. So calculate the resistivity. There's not too many equations in this class that have resistivity in it. And the main one is R, resistance, is equal to resistivity times length divided by area. So if I want to calculate resistivity, I need to measure somehow R, L, and A. So I'm going to show the most common solution to this that I was anticipating, and I'll explain an alternate one as well. So the easiest way I'd think is just create a big series network of these resistors to effectively alter L, and just make sure you took the area at least once. So measure the cross-sectional area of one resistor using a ruler. So you just do length times width, or length times height, I guess. Then you wire a set of the resistors in series, measure the total length L. You use a multimeter to find the resistance R of the network, and you repeat for multiple resistors to reduce uncertainty for collecting data using a range of effective resistor lengths L. So here's where you get points. So first, you get 1 point for using the multimeter to measure resistance R. So pretty straightforward that we needed that. You got 1 point for any experiment that used the multimeter to find resistance in a valid way. And then you'd get a second point for somehow measuring measuring L and or A in a series of trials. So you have to indicate that multiple trials are being done. And here I did that by saying repeat for multiple resistors. So now I have a data table of R and L with a constant A. So again, I always let the equation guide us here. So it's usually not going to be too crazy how you have to analyze it. So here we have the equation R is equal to resistivity times length divided by area. And I used capital L here, and I probably shouldn't have. And we want to find resistivity. So the thing we had was L, that was our variable, and A was some constant we measured. So I can actually rewrite this equation as R is equal to resistivity times the quantity length divided by area. So as a result, we're just going to graph R versus L over A, and then the slope is the resistivity. So that's how you get your 2 points. So first, you pick a valid relationship that will create a straight line. So here I picked R and L over A. You could pick R over L, you could pick R versus L, or R versus 1 over A. RA versus L, I've also seen. Anything like that, as long as it's a linear graph that works, and then a correct analysis. If you graph the wrong thing, no second point. Also, feel free to comment or ask me if you have alternate solutions you'd want to check out. I imagine there's things I haven't thought of that solve this. Now we have the second part of the lab question, which has us looking at an experiment that we did not do, or we did not create, and we have to actually analyze it. So here we have just a discharging capacitor where a group of students are using a resistor at different resistance settings and measuring how long it takes a capacitor to halfway discharge through the resistor, or essentially measuring its half-life. So we're given the half-life and we're given the resistance. So we know that this is going to be like a time constant RC circuit type thing. So I'd start from the fact that for a discharging capacitor, the voltage varies via a relationship that looks like this, where it's an exponential decay that's proportional to e to the minus t over RC. And we want to find the time when the voltage is exactly halved. So 1/2 V max is equal to V max e to the minus t over RC at t 1/2. And notice the V max actually cancels. So you'd get 1/2 is equal to e to the minus t over RC. You'd log both sides and get ln of 1/2 is equal to minus T1/2 times or divided by RC. So the half time is going to be equal to RC times the natural log of 2 after flipping the logarithm. Of course, you could write negative RC ln 1/2. That's totally valid also. But the thing to notice from here is that the half-time, T1/2, is actually proportional to the resistance itself. So it actually is dependent on this time constant itself, RC. It just has this ln2. So a lot of people actually graph the correct relationship, but for the wrong reason. They just think that this isn't T1/2, but it's actually tau, and they just graph thinking this is the time constant, and their final answer will be off by a factor of ln2. But to get your first graphing point, all you have to do is correctly identify a straight line relationship. So for this one, you just don't have to transform it at all. So I'm going to graph the resistance R on the horizontal axis and the half-time T1/2 on the vertical axis. I might also choose to instead graph R ln2 on the horizontal axis instead, so that my slope is just the answer. So now we're going to plot the data points for this, and we have to make sure that we scale our graph, we have to put units, all of that fun stuff. So my T1/2s are in seconds, so this is my half-life in seconds, and then down here this would be my resistance in millions of ohms. So the capital M means mega, or 10 to the 6. So I'm going to count by 20s on the vertical axis, because I just go slightly under 100 there. And always make sure to include 0 down here if this is actually 0. So I get 20, 40. Please actually draw out your whole scale like this. 60, 80, and then 100 is up there. And then for my R's, my R ranges from like 1 to 5. So I'm just going to do like 1 ohm, 2 mega ohms, 3 mega ohms, 4 mega ohms, and 5. And again, you're just trying to use at least half the available grid space here. So that's sufficient for using half the grid. All right, now we're going to actually plot the data points. And by we, I mean I am going to quickly pause this and do that, because I don't think you want to watch me plot points for a minute here. So I'll be right back on that. All right, so we are back, and I have plotted my points. So now we're going to draw a best fit line. So again, you always can bring a ruler to the AP test, so please do that. So I'm going to try to draw, to the best of my ability, a line that appears to do at least half the data above/below. Don't force it to the origin if it doesn't look like it belongs there. Ours looks pretty close, but I'd say something like this maybe is a pretty good best fit line. And I always recommend just doing it with Desmos and how almost like copying off the screen to help plot your points here, because if you use the auto scaling on Desmos, it'll work. So this is actually worth 3 points, regardless of what relationship you graphed. If you plotted the points correctly, that's a point. If you drew a appropriate best fit line, meaning something that's reasonably best fit, that's 2. And then for your third point, you had to scale your axes using at least 50% of the grid space with units. So please check that you have accurate units here, especially if you did some weird transformations. It doesn't show up here, but will in the future. So this is out of 3. I always suggest we start with this question, because these are very gettable points, even if you graphed a wrong relationship. So now, using the best fit line, calculate C, the capacitance. So we said that the half-time was equal to RC ln 2, which told us that T1 half, which was on the y-axis, was equal to C times ln 2, which is a constant, times R, which was what was on the x-axis. So this means that our slope is C times natural log of 2, or the capacitance is just going to be the slope of our best fit line divided by natural log of 2. So doing this, you do have to write that you use technology to get the slope. I'm just writing Desmos, and I'm actually just going to write the equation of the best fit line. So Desmos tells me that my line is 19.2x minus 4.12. So I'm just going to plug that in to my calculator, and dividing 19.2 by the natural log of 2, wherever that is on Desmos, there it is, ln of 2, I get 27.7 microfarads as my final answer for this. So your 2 points on this, you get 1 point for attempting to relate the slope to the equation tau equals RC. So for attempting to relate the half time to tau, you get 1 point, and you get another point for a reasonably correct final answer. So approximately in the high 20s of microfarads. That's out of 2. And a correct answer does have units. So this would also be 2.7 times 10 to the minus 5 regular farads. And I used the micro here because I was using this mega ohm unit. So there was a times 10 to the minus 6 that was sort of being carried through everything. And I just kept that last. If you didn't know that, you could have just left this as a slope unit, which would be seconds divided by mega ohms. So you could have actually left this as 27.7 seconds per mega ohm, which is the same as a microfarad. So the lab question's worth 10. 2 for design your own experiment, 2 for analyze your own experiment, 1 for the correct linear relationship, 3 for graphing a relationship properly with the best fit line, and 2 for the correct analysis of the experiment. And now to finish, we have question 4. So we've seen that we've gone through our induction, magnetic fields, and circuit questions. So this actually leaves the electrostatics question last. So this is going to be either Coulomb's law or Gauss's law. So in the diagram shown above, a conducting sphere of uniform volume density, rho m, so a mass density with volume, holds a charge uniformly distributed across its surface with charge density sigma. So it has mass with a rho, because mass is distributed all throughout the solid sphere, but your charge density is not a rho, but it's actually a sigma, because it's conducting. So all charge goes to the surface for a conductor. And then it's suspended at rest from these parallel plates that produce a constant field E to the left. And as a result, the sphere is going to hang from the ceiling and make some angle theta from the vertical. And assume that the sphere's radius is really, really small compared to the plate separation, so we don't have to deal with any of those effects. So first, we have to do the first step of the qualitative-quantitative translation, which is the qualitative part. So qualitatively, we need to figure out what is happening if the conducting sphere has the same mass and charge densities. So the densities are the same, but twice the radius, indicate how theta will change. So what will happen with a sphere of double the radius, but the same parameters? So this is really tricky, and we have to think about scaling laws here. So what essentially we're doing is we're taking a sphere and we're doubling its size. So if we double its size, its radius goes to 2r. Its area is going to square, because area is proportional to square, but its volume actually gets multiplied by 8, because volume scales via a cube. So actually, by doubling the sphere size, anything related to volume is going to go times 8, and anything going with area is going to times 4. So as a result, we're actually going to see that the sphere is gaining weight much faster than it's going to gain charge, because it's a cube versus a square, because the charge is stuck on the surface, but the mass is distributed throughout. So actually what's going to happen is the rope is going to have to work harder to balance the mass than it does to balance the charge, because we see the angled tension here. It's balancing the E field one way, and it's balancing the weight force the other way. So theta will actually decrease because the angle is going to become smaller because the string will be more vertical. So here's our explanation on this. The tension in the string must balance both the gravitational force and electric force acting on the sphere. 1 point if you said that, regardless of checkbox. You also get 1 point for selecting the theta decreases checkbox. So if you said anything about balanced forces, or the fact that there are two forces acting on the sphere that need to be balanced, that's 2 points. That's one of your justification points. Now, you get a second justification point for saying that the gravitational force is going to increase more than the electric force. You don't need the exact factors. You could just say volume increases faster than area or anything like that. Maybe this is slightly dubious for a QQT that I even include this factor of 8, because I was supposed to not manipulate equations, but I'm just saying that gravity, the weight force will increase by a factor of 8 since mass scales with volume, but the electric force will only increase by a factor of 4 since surface charge scales with area. So thus, there's more of a weight force to balance than an electric force. So that's going to cause theta to decrease. So this is out of 3. 1 for the checkbox, and then those 2 justification bullet points. If you said either of those, it's possible to earn justification points without the correct answer. Now, for the part 2, quantitative, where we actually have to derive an expression for something. So suppose the conducting sphere is radius r, derive an expression for tan theta in terms of, I made this joke in class, so I'm going to just say it again. In terms of, we got the whole fraternity here. We got theta, rho, sigma, all of that. So what we have is acting on our sphere. We have a weight force, mg. We have an electric force, QE. And then tension has to balance both of those put together. So the tension force Ft has to balance both of those put together. And we want to find this angle theta, or at least the tangent of it. So first, we're going to start from Newton's second law, because this is a balanced forces equation. So starting from Newton's first law or second law, depending on how you see it, I know that the force is balanced. So I could either write balanced forces or sum of the forces is 0. So what this means is that the x component of tension needs to balance the electric force And the y component of tension needs to balance the gravitational force. But unfortunately, we don't have Q or M, so we actually have to figure out both of those. So first, for Q, we're given the surface charge density sigma. So Q is just going to be sigma times the area, which is the surface area of a sphere, 4 pi r squared. And then for the mass, M, mass is density times size, but we're given a volume density. So density times size. We're just using the volume of a sphere in this case. 4/3 pi r cubed. So again, we can always find the total amount of something by either multiplying density times size for the correct parameters. Maybe you have to integrate it if it changes. And then we can just find tan theta. So tan theta is just opposite over adjacent. So it's just going to be ftx divided by fty, which is 4 pi r squared sigma e divided by 4/3 pi r cubed rho g. And I'm actually going to simplify it a step further because we get some cancellations. So I see the pi's cancel, the 4's cancel, the 3's come to the top. So I'd get 3 sigma e divided by rho times g, and then 2 of the r squareds. The r squared on top cancels 2 of the r's on the bottom, so I'm left with a factor of 1 over r out front. So that's our expression for tan theta. 3 sigma e over rho g times 1 over r. And then we just have to answer the consistency question, whether this works with our part A. So here's your 3 points for the derivation. First, anything about Newton's second law, about balanced forces. Next, you get a point for correct computation of Q and M. So you need Q and M correct to get the second point. So sigma times 4 pi r squared and rho times 4/3 pi r cubed. So you need Q and mass correct. And then your third point is a correct final answer. Or we'll say, a consistent final answer of substituting for something that's equivalent to taking the tangent of QE over mg. So now we just have to answer, is this consistent with part A? So we said that theta should decrease. And I would definitely say that if r increases, theta decreases in this problem, just based on my formula. And why? So yes, they're consistent because we see that tan theta is proportional to 1 over r from part B. My derivation says tan theta has this 1 over r out front, so as r increases, tan theta is going to decrease, which is the same thing as saying that theta is going to decrease, which is as expected. So that concludes that. So you get a point for a valid consistency claim and a valid justification. So it does not have to be consistent to get the point. If you messed up one of your derivation or your explanations, it's not consistent, and explain why. You can still earn both part C points, you just miss out whatever you did wrong on the previous part. So this is out of 8. So 3 for the qualitative, 3 for the quantitative, 2 for the translation. So that sums us up to 40. And with that, we are done with a full E&M practice test, and one that I think is very challenging. So this does a good job of handling at least most of the course content. Again, I think this is a really fun set of questions to extend your abilities and kind of look at different things here. All right, so that's our E&M test.